Hi all, my name is Jeff Hasboon and I'm a postdoc at the University of Washington, Bothell. And I'm going to summarize some of the important findings from a paper called Model Dependence of Bayesian Gravitational Wave Background Statistics for PTAs. And the archive number is right here. And since I'm going to try and keep it short, if you have any questions or want to see any more background information, that is the place to go. And you can obviously email me or ask me any questions if you'd like to know more. So the topic of this paper really is about red noise. And the important thing to know about red noise here is that we can model the gravitational wave background that we're looking for as our signal as a red noise process. It just means a stochastic process that has more power and low frequencies. And of course, the background is spatially correlated, but I'm not going to talk about that too much here. But also, we can see this kind of red noise in our individual pulsars from other sources. That's as important as well. And so, in thinking about those two things, we're going to talk about a bunch of simulations that we ran to try and understand how our choices about red noise affect the gravitational wave background searches. So this was motivated by early analyses of the Nanograv 12.5 year data set, where we were finding a most likely amplitude for the background that was higher than our 95% upper limit from the 11-year analysis. Now, that's not completely untoward or unheard of when you add more data to an analysis. It is possible for you to get a signal a parameter estimation above your upper limit, but we really wanted to understand what the impact of our assumptions about red noise were making on this. You can make a few different assumptions about red noise, and those will sort of affect what you choose for the red noise priors and things like that. So all the pulsars could have measurable intrinsic red noise. None of the pulsars could have measurable intrinsic red noise. We know that's not true because there are at least a couple of pulsars that have measurable red noise that is definitely too big to be the background. And then number 3, though, is some pulsars have measurable intrinsic red noise. And you can tweak all of the levels of these by choosing what prior you're putting on the amplitude for the red noise in the Bayesian sense. So number 1 has been what we think of as our conservative choice. We just assume all the pulsars have some amount of red noise that we can measure. But 2 actually gives the largest upper limit. So in some sense, it's the most conservative. If you assume that any red noise you see is due to the background in an upper limit sense, not a detection sense, then you're saying, well, I can't actually say that this isn't the background, so you're getting a number that's the biggest number, so hence the most conservative. It's probably wrong, but maybe in some sense the most conservative. Number 3 is probably the most accurate, which is that we have some pulsars where we can measure the intrinsic spin noise from them or some other process, whether it be asteroid belt or something, that's giving us some kind of achromatic red noise. So what to do? We ran a ton of simple simulations where we only inject a gravitational wave background amongst the pulsars and white noise that's commensurate with the TOA errors. And then we did this with all of our standard analyses and some non-standard analyses, one of which is what we call this dropout red noise model that I'll talk about a little bit later. And so the results are all shown in aggregate. So we ran 400 realizations of each of the different types of analysis with these 400 different injections. And we did the analysis at different slices of the data set. This is 11 and a half and 15-year slices. You really only need to look at 1 year and compare amongst that. The conclusions are basically the same. On the left, we used a log uniform prior for the amplitude. So that would traditionally be what you would use for a detection run. And then the different plots show either no red noise models, which is the blue. So that's basically the model that we use to inject. We're using to recover, right? We inject a gravitational wave signal, no red noise, and we get back something that we expect. These are all aggregates, so the violins are showing the distribution of the median values. So this is the distribution of 400 different medians. The horizontal whisker is the median of the medians, and the vertical whisker shows the inner 68 percent credible interval for these. And so when you use the same model to recover, which is the blue, you basically get what you expect. However, when I include a red noise model, even with it, so on the left here we show it with in the orange and green, that's with a log uniform prior on the red noise. We get slightly less, we get amplitudes that are slightly less than the injected value. That's the dashed line, of course. On the right, we are using a uniform prior in all of these on the amplitude of the background. And we actually, in the purple, you see this strongest effect here, where we use a uniform prior on the red noise. Now, we'd never use this analysis for a detection run, but we do use it for the upper limit. And so this kind of gives a hint of what I'm going to show you in a second, which is what happens in the upper limits. In both cases, no matter what the prior is on the amplitude of the background, if I use this dropout analysis, where I let the analysis turn on and off the red noise model on its own, then I get the red and the brown violin plots, which basically return the same distributions of the medians that you would get if you used the correct model, which has no red noise model in it at all. So what's happening here, right, is that we have this red noise sinkhole, and so we get power going into the red noise models for the single pulsars rather than going into the full common signal. And so we can fix that by having this dropout analysis. The effect in these simulations was definitely the most drastic when we looked at the 95% upper limits. And on the left here, these are now the distributions of the upper limits from a number of sets of analyses. And these are all run with a standard uniform prior on the gravitational wave background, and then different priors on the amplitude. On the right, I'm basically showing the rightmost violin plots from the left plot. So these are the posteriors from the blue is just if I only have a gravitational wave search, no red noise model. The orange dashed line is if I have the standard power law red noise fit for each pulsar, but with a uniform prior for the upper limits. Well, the uniform prior really pushes the power into the single pulsar models. And so I only get about 50% of the upper limits being above the injected value. And again, we're never guaranteed this. This is called the coverage of an analysis. We're never guaranteed that 95% of your upper limits should be above the injected value, but it's good to know where we stand. Okay, and so as you can see on the left from the red violin plots, we can fix this with the dropout analysis. And getting the spinning wheel of death. Okay, this is a summary of the dropout analysis. I'm going to go through this one quickly and show you the real data in a second. But basically, the dots tell us from where they are vertically how often the dropout red noise model is turned out. So if the dot is at the top, it's at 1. It's a fraction of it's turned on all the time, and if it's at the bottom at 0, then it's turned on none of the time. The top is the dropout analysis when there's no red noise injected. So in most realizations, most of the time, the red noise is turned off. The bottom is a set of simulations that we did where we inject red noise into 4 of the pulsars, and I'm best betting you can guess which 4 it is, 0, 16, 24, and 28. And depending on what slice you're at and the index and the spectral index and amplitude of the red noises, you get it turned on more often as we go further into the data set. So this works really well. It actually does turn on when there is red noise, as we would hope. Okay, this is the results from the 11-year run on the 11-year data set. And what's great to see here is that things basically match the single pulsar noise analyses. The color coding and shape of these tells us whether the red noise was significant, that's the orange circles, or not significant, that's the blue squares, and the green is somewhere in between. So these are the single pulsar noise runs telling us that the red noise is significant and it's turned on in most of the pulsars in the full gravitational wave analysis. The only one it's not is 1909, and in the 11-year data set, go figure, the red noise does look like a gravitational wave background. And so I think a lot of us are hoping and being optimistic that that background we see in this single pulsar is the actual background. And since 1909 is one of our most sensitive pulsars, hopefully that is true. And then, of course, this does affect the amplitudes that we see. And so we don't get a ton more significance in the detection, but this is a full Hellings and Downs run here. And with the dropout analysis, what you see is that the amplitude you get from the posterior, the maximum amplitude anyways, is higher. And in fact, this is much more in line with the 12.5-year results from Nanograph. So again, if people have more questions about this, feel free to ask me. Also, you can consult the article on the archive, the identifiers there at the bottom. Thank you very much.